In this video, we will evaluate a definite integral by using a limit definition with the right sample endpoints. We will use the limit of the Riemann sum. We will not use the fundamental theorem of calculus. Okay, let's start with this question. Evaluate the definite integral from 1 to 6 of the function x minus 1 dx. We can definitely do this question quite fast, and I can possibly do this just to double check if our long limit definition way is correct. We do have a function x minus 1. I can draw this function, -1 and 1, and the definite integral, just to remind, between 1, okay, and let's pretend that this is 6, between 1 and 6, it's basically the area under the curve. We will call net area. In this case, everything is positive, function is positive, between 1 and 6, and I can say area. Value of the function for 6 is 6 minus 1, 5. And we can see how quickly we can get that area because it's basically a straight lines. Each side is a straight line. It's a triangle. 1/2 times base times height. 1/2 base of this triangle is the number of units between 1 and 6, 5, and height is the value for 6, is also 5. Okay, 25/2 area, 12.5. Okay, so we did it. Unfortunately, that's not the way that we were asked to do, but this is definitely the correct answer. Let's see if we can use the limit of the Riemann sum. Definite integral is defined as a limit of the sum of the areas of rectangles, starting from 1 to n, and n goes to the infinity. F of x sub I times delta x. F of x sub I, the value of the function, is the height, delta x, the base times height. Sub sigma means that we're adding all of these areas, and we do have infinitely many of those rectangles. Okay? Let's compute delta x. Delta x is the entire interval between 1 and 6, which the length of that interval is 5, and we will divide by n, 5/n. Okay, let's start our evaluation. Limit as n goes to the infinity, summation from 1 to n, and our function is defined as a x minus 1. It will be x sub I minus 1. And delta x is 5/n. Okay. Limit as n goes to the infinity, sigma, summation from 1 to n. We also need the formula for the x sub I. Let's do it here. The formula for the x sub I, for the sample point, for the right end sample point, is a plus I times delta x. Yeah, we do remember from the class the explanation. A is the beginning of the interval, 1, plus I times delta x. Delta x is 5/n times I. Okay, let's substitute. Instead of x sub I will put 1 plus 5i/n, and we also have minus 1 as a part of the formula, and times delta x. That's our additional formulas. Oh, luckily, I can simplify. Limit as n goes to the infinity. Let's see what we have. We will have 5i/n times 5/n, 25/n squared, and I. All right, yes, I just multiplied these two items. Now, limit as n goes to the infinity. With respect to the sigma, 25/n is just a constant, and I is changing from 1 to n. And this is the addition of the counting numbers. We know the formula, which we will use it now. The formula for this is basically n times n plus 1 over 2. Yeah, you remember the little Carl Gauss discovered that formula. And when we look at the expression, the rational expression that we got, we have n squared and times 25 when I distribute, and the rest of the items we're not really interesting because we have to actually find just the highest power. And oh, did I lost something? Oh, I do lost n squared. We can see n squared, n squared, n squared, n squared. We will have 2n squared. Okay, and this limit is, we have function n squared, the ratio of the leading coefficient 25 over 2. And we can say that's the correct answer, because we can basically use the area of the triangle, but we went through the nice limit definition. I can also apply the fundamental theorem of calculus, but if we still don't know this, we will learn later. Okay, that's the fundamental theorem of calculus are telling us a couple of things about the anti-differentiation integration, and it's basically the shortcuts that we will like. Integral of x is x squared over 2, integral of 1 is x, because derivative of x squared over 2 is x. Derivative of x is 1, negative of course. And then we will apply the limits from 1 to 6. We will substitute 6 squared over 2 minus 6, and then we will substitute 1, but we will subtracting. 1 squared is 1 over 2 and 1. And we will have 36 over 2, 18, minus 6, minus half, plus 1. And this is 25 over 2. You may pause the video and check, but I did check. Okay, we have actually 3 different ways, but the long way was the required way. Okay, let's do the next one the same way. Then we will have no problem completing our assignments. Okay, now we have the same thing, oh, that's typo. Definite integral between 0 and 2 for x cubed plus 5. This one, unfortunately, we will be not able to use the area because function x cubed times 4 is a little bit slimmer, and it's just x cubed shifted 5 units up. That means function looks something like this. Okay, our function is 4x cubed plus 5. And the integral between 0 and 2 will be represented by that region. And we can see the top of this region is curved. We can't really use like the geometric shapes. Value of the function for 2, I don't know, but maybe we can calculate just to make sure that we can substitute 2. 4 times 2 cubed plus 5. 4 times 8, I believe, 32 plus 5, 37. Yes, we did it. Okay, but that's, I think we cannot really go this way. The area, yes, that area is, we can use fundamental theorem of calculus, but we still don't know all of the formulas. Maybe at the end I can do it, and then later you will compare. Let's do the nice limit of the Riemann sum. Definite integral is the limit of the sum of the areas of the rectangles, height times base, delta x is base, and we have the rectangles from 1 to n, and number of rectangles is huge, infinity. Let's evaluate for our function. Then our function is defined as a 4x cubed xi cubed plus 5. Delta x, now delta x delta x is the length of the entire interval between 0 and 2 is just 2, and we're dividing by n rectangles, 2 over n. Okay. We also need the formula for x sub I. Can maybe substitute directly. X sub I is a, which is 0, plus I times delta x. Delta x is 2 over n times I, plus 5, 2 over n. 0 is actually helping us because we may skip that 0. Let's simplify. We will have just 2i over n cube. 2 cube, I cube, n cube, plus 5 over 2 over times 2 over n. Okay, let's see. Yeah, and we like this nice order of each line. Yeah, alignment, limits, sigma, everything has to be nice and clear. Okay, what we have? We do have 2 cube is 8. 8 times 4 is 32. Yeah, we did this computation. And over n cube and I cube. And plus 5, 2 over n. Okay, let's do a little bit of movements. 2 over n, I can distribute, but I can also put in front of sigma because with respect to sigma, it's a constant, it's not changing. And I can also rewrite this as a summation of 32 n cube I cube plus the summation of 5, which is also a constant. We need a couple of from 1 to n, and that's because 2 over n is, I kind of distributed sigma. We not. The sigma, the summation of the addition is just the addition of 2 summation, addition of 2 sigmas. Okay, limit as n goes to the infinity, we will need this. And now what we have? 32 over n cube, it's a constant with respect to this. That's we do have I cube. Okay, now summation of 5. 5 is constant, but this means that we have to add 5 plus 5 plus 5 n times 5n. Okay. I believe I will need an extra page. We know that practice because I will not squeeze it. Okay, so what we have? We have a limit as n goes to the infinity, 2 over n, and 32 over n cube, right? And now we need that formula. I cube, the summation, the addition of cubes of the counting numbers. I hope we remember n plus 1 over 2, but everything is squared. I can do squared, or I can square each factor, squared, squared, and squared. Because we have that formula. And then 5n, I can simply copy 5n. Okay. Let's see. We can distribute this. Okay. We can definitely distribute. Let's check. Limit as n goes to the infinity. We will have 32, and okay, I can write this for now, and n to the power of 4, 2 to the power of 2 is 4, and actually 2, I forgot that 2. Okay, plus 2 over n times 5n, which we can cancel out. Okay, almost. Let's look at that ratio. We have 4n to the power of 4. And when I distribute n to the power of 2 and another n to the power of 2, we will have also the leading function n to the power of 4. And the leading coefficient is 32 times 2, 64. Okay, and this is 2 times 5, 10. Okay, the same function, n to the power of 4 over n to the power of 4, 64 over 4. Actually, I can write 16 because 2 minus 6, oh, actually 16 plus 10. The final answer is 26. Perfect. We did it through the nice limit of the Riemann sum, limit definition. And as promised, I can use the shortcut, but we still don't know how to do it. The integral was from 0 to 2, and function was 4x cubed plus 5 dx. Because integration is the anti-differentiation, the antiderivative of 4x cubed is x to the power of 4, because derivative of x to the power of 4 is 4x cubed. Antiderivative of 5 is 5x, because derivative of 5x is 5. And that's the fundamental theorem of calculus, which this will be proven later. We can substitute to the upper limit instead of x, and we can substitute the lower limit, which actually is nice because it's 0. That's 0. 2 to the power of 4 is 16. 5 times 2, and yes. And of course, it's a little bit more efficient, but we still need to understand the limit definition way, because that's the essence. And one more. Okay, let's do one more, because this one will be still maybe a little bit longer, because we will see the kind like one of the formulas. Okay, the same thing. We can't really use the areas because function is quadratic. We will have like a curve, not the straight line. Okay. Or you may pause the video now, and you can try to do this function, this integral, definite integral, okay? And then you can compare with my solution. Hopefully we will match. Limit of the sum f of x sub I times delta x. I is changing from 1 to n, and n goes to the infinity. Okay, now we are more, we can do faster because we know all of the formulas. Okay, our function is this one, integrand, function that we're integrating. 3 x squared xi squared plus 1 delta x. Actually, we can compute delta x. Let's use that space. Delta x is the length, the number of units between 2 and 5, and we will divide by n, 3 over n. And we will need x sub I. Okay, that's times. So we do have this formula. X sub I is using the right endpoints. It's a plus I times delta x. A is 2 plus delta x is 3 over n times I. Yeah, I always change the order. Let's substitute. I is changing from 1 to n. Okay, we do have 3. We have x sub I squared plus 1 times delta x. And this is 2 plus 3i over n squared. Okay, and that's what I said. We do have like the expanded form, and we have to square it. Let me write this maybe here. When we will take that, actually x sub I squared, because we have this 2 plus 3 over ni squared. Okay, okay, that means I will just use that formula, a plus b squared. Okay? You can FOIL a plus b times n plus b, but we know that we will get a squared 2 times ab plus b squared. Yeah, we remember this formula. Okay, that means let's see what we will have. We will square 2, 4. We will multiply 2 times 3 over n times I times 2, which is 6, 12 over n I. And we will square the last term, 9 over n squared I squared. That's our x sub I squared. Let's put it to the formula and see what we will get. Okay, 3 times 4 plus 12 over n I plus 9 over n squared I squared, n plus 1 times delta x 3 over n. What's the easiest way? I believe we can distribute that 3 because we don't want to lose it. Yeah, each algebra arithmetic step has to be correct. 3 times 4, 12, 3 times 12, 36 over ni. 3 times 9, 27 over n squared I squared. N plus 1. And the only like terms is, we can see is 12 and 1. I can possibly say 13. I hope we will be okay with this. And that's gone. Yeah, I added 12 plus 1, 13. Okay, and what we can do now, we can put actually delta x in front. Yes, we remember this. Let's do it. Oh, we need extra page. Let's add quickly the page and let's finish, and that will be our last. Okay, let me copy this limit. I mean, not copy, just we can put our delta x 3 over n in front of the sigma, and then we will have sigma, the summation from 1, and we can actually apply sigma, the summation, to each term, 13 plus sigma, that's actually I, correct? I is changing from 1 to n, and then what we have, I think we had 36, yes, 36 over ni, and then we will have, I is changing, 27 over n squared I squared. If we can check, 37 over n squared I squared, 36 ni, and 13 because I did add 12 plus 1. Okay, now limit as n goes to the infinity. Okay, and let's see, 3 over n, and now 13 plus 13 plus 13 plus 13, 13 times n, 13 times n times 13. Okay, now 36 over n is a constant. We will just add I. I is changing from 1 to n. 1 plus 2 plus 3 plus 4 plus n. We know the formula. 27 over n squared is a constant with respect to the sigma, and we just adding I squared. Okay, now we need the formulas. 13n, 36 over n, and that formula, just the addition of the counting numbers, is n plus 1 over 2, and this one will be 27 over n squared, and the formula of the square numbers is n plus 1, 2n plus 1, all over 6. Okay. What we can do, let's distribute 3 over n, because we need the proper, and this will be 3 over n times 13n, the n's are cancelled. This will be 36 times actually 3, because it's 3 over n, and 2n. Or maybe, let's keep the nice, doesn't matter. It was 3 over n, and that's 36, okay? But from the green formula, the n squared will be the highest power when we distribute, and we don't need the other one. Now we have 3 over n times 27 over times n squared, and we also have 6. Okay, and the green formula will give us n times 2n, 2n cubed, and the rest of the terms will have lower power. We don't need this. Okay, let's actually evaluate the limit. Limit of 13 times 3 is 39, constant. This one we will have n times 2n is 2n squared, the same degree, just the leading coefficient. 3 times 36 over 2. Maybe we can simplify. Dividing by 2, it will be 18. Okay, let's do this way. 3 times 18. And this one will be again n cubed, and in the denominator we also have 6n cubed. I can just rewrite nicely 6n cubed. And we can simplify. Let's simplify, then we can avoid fraction. N cubed and n cubed, that's when we just need the ratio of the leading coefficients. The limit at infinity, of course. Actually, 2 times 3 is 6. We can cancel out 1, 1, and 1. Oh, wow, 27. Okay, and I believe that's the correct answer. 39 plus 27. Actually, let me maybe do here, because I can still use the fundamental theorem of calculus. I hope I can have enough room. All right. Oh, I wish you will help me. What we can do, 39 and 27 is 50, 66, and 18 times 3 is 30 plus 24, 54. Oh, nice, 120. Okay, we did it with a small help of my dog. Okay, let's apply the fundamental theorem of calculus. The integral was from 2 to 5, and function was defined as a, let me check. Oh, 3x squared, right? 3x squared plus 1. But that's not required for this question. Okay, I'm just checking. Antiderivative of 3x squared is x cubed, because derivative of x cubed is 3x squared. Antiderivative for 1 is x, because derivative of x is 1. And that's the fundamental theorem of calculus. We will substitute the upper limit instead of x, and we will substitute the lower limit, but we always subtract the number. Okay, 125 plus 5 minus, that's cube actually, minus 8 minus 2. 130 minus 10, yes. Okay, yes, definitely correct. But the bottom way of solving the problem, we will still practice in our next classes. Thank you. Enjoy your limit of the Riemann sum. That's the definition of a definite integral. Thank you.